So we went ahead and we put our grout column in there, and you see the black lines in between those white chips. That's neat cement. And you see how the neat cement has just divided the chips and forced its way and intruded right through a partially hydrated bentonite chip seal. Not only did it do that, it kept migrating right down into the gravel pack. You see the gray matter in between the grains of sand? That's our neat cement. And if you keep watching it, you see the cement cracks. So now we have a product that's designed to protect the ground water, full-length grout, that has penetrated our primary seal, gone down into the production zone, and cracked. We have a pathway. What we're recommending is we have to protect those chips with a real fine blotter sand, so that keeps that neat cement away from the bentonite. We won't have that chemical reaction between sodium and calcium. Slow that column down and let it solidify before it gets into our production zone. So grout compositions. Remember that grout that was just as good as the rest of them? Well, it was. That less than 20% was just as good as a 20% or a 30%. Problem is, none of them performed worth a darn. The 16% grout cracked quicker. Took the 30% grout a little longer to crack, but they still ended up in the same position. Pure bentonite solids as a slurry will not rehydrate when they're damaged. They are inadequate in the Vedas zone because of the wicking effect. The Vedas zone has a dynamic of it's always pulling for water. And if it pulls water out of it, let's say a 20% water slurry, and you have 80% water slurry, 20% bentonite, you pull the water out, you've got 80% open area. And that dynamic goes on 24 hours a day, 7 days a week, forever. So a bentonite slurry in that unsaturated zone is not going to provide the protection we're looking for. Now the bentonite chips, here's another unexpected result. The bentonite chips do crack, but we discovered they do rehydrate. They're a raw bentonite product. They're over 65 to 70% reactive solids in the bentonite chip. And that Grand Island site where we had high fluctuations of groundwater, we saw in the end of the irrigation season that the grout of the bentonite chips would pull apart. And by the springtime, when the water table came back up, they'd come back together. And we saw that very consistently for 8 years. It never left that dynamic. So we feel really great about the possibility of a bentonite chip rehydrating and providing that maximum protection. But they're time consuming to put in the borehole, takes a long time to place, and they can be very difficult if the borehole's not big enough. The cement-based grouts. We really like cement-based grouts for structural stability. A cement may crack on you, but it won't leave. If a bentonite cracks and you have that 80% void space, it's gone. A cement stays solid in the borehole, it's where you left it. So we like it for structural stability on the top of the borehole. It solidifies the casing, it prevents the casing from cracking if it's impacted at the surface, but we also discovered that cements do not bond to PVC, which is something else the industry didn't expect. Well, and we'll talk about that in a later slide. So what do these results really tell us? All right? What they tell us is portions of the borehole are adequately protected, portions of the borehole are not adequately protected. Things are different than what the industry really thought. So in 2005, the task force asked the University of Nebraska to study this, just the unsaturated zone. And a man named Will Myers for the University of Nebraska determined that the biggest components that affect grouts are the particle size of the unsaturated zone and what makes up that particle. If it's a grain of sand or if it's a grain of silt, it is a total different dynamic. The sand doesn't absorb anything, but the silt will. And the moisture content of that Vedas zone, annual precipitation plays a real big role in that. If the saturated zone is constantly dried out like we have out west, and it's a silt and it's a clay, super absorbent material, and it's disastrous to a high water slurry. If it's a clay that's in the northeast, that's a real tight clay that gets a lot of moisture, you have a little bit better result for a high water slurry. So now we've narrowed our focus. If we want to provide maximum protection to the groundwater, we've got to focus from the groundwater table up and find out just what's going on for that dynamic. So that leads us into the Vedas zone study of 2008 and 2009. Now what's different? What is different about the Vedas zone study? Well, a couple things. Like I said, we're just looking at the water table to the surface. And now we're looking at different methods of construction. The grout study was based on mud rotary, because we're a mud rotary state. That's how our wells are drilled. But because we're having such a challenge with our environmental wells, we decided to look at hollow stem augers and direct push. And this is technology used for constructing, monitoring, and cleanup wells. So we have different methods, and now we're looking for different recipes. Began planning this in 2007, and we came up with 4 parameters we have to match for the Vedas zone study. We'd have to find materials that would resist cracking, be easily placed, be economical, and readily available. Okay, if you can't match all 4 of these, it's not going to work for us. And early on, we determined we could find materials that would resist cracking. That's not the problem. The problem is we couldn't afford them, we couldn't get them, and nobody had the equipment to place them. So we had to find materials in our state for our contractors that would match all 4 of these parameters. And here was, the state had 3 designs they wanted to look at. Our environmental folks had 4 designs. They were really concerned about their industry. Our partners in this from the bentonite industry was Wild Bend, Setco, and Baroid. Each had 3 recipes to look at. The direct push folks had 2 for a total of 18 wells per site. And then, as a concern for our geothermal contractors, GeoExchange, we went back to 2 sites in the southwest and in the northeast area of the state. And we went back and looked at gravel packing these loops and putting chips around the top for 2 reasons. We already had wells that were constructed like this, and we had to study this to see if we had potential problems in the future. And 2, we had to see why these sand-packed wells performed a lot better than the geothermal grout wells that were grouted to the surface. So the mixes the state wanted to look at. Mix number 1 is a recipe we got from the state of Kansas. And this came right out of their oil patch, and it was basically a cement bentonite with a lot of high solids in it. 100 pounds of sand for a bag of cement and 5 pounds of bentonite. The next thing our contractors wanted us to look at was drill cuttings. They said, hey, put back the material in borehole you took out. If you're trying to match things, it's got to be a natural match. So we did. We studied drill cuttings. Then the third thing we were really concerned about was our standard for constructing domestic wells in Nebraska. And this is where we would gravel pack to within 10 feet of the surface and top it off with a chip seal. We had to see if those grouts were performing adequately to protect our citizens. The environmental folks, they had the answers. They said, Tom, mix number 1, mix number 2, that's going to do it. That's going to be it. We studied it. We had great success over the years. We really like this. But in order to find something else, just in case, they came up with a really high solids slurry of 450 pounds of sand for 1 50-pound bag of bentonite. That's a 9-to-1 ratio. Okay, that's really high solids. And then they came up with a dry mixture. They're going to mix 3 parts of sand with 1 part of bentonite, and they're trying to match the grain sizes. The granular bentonite's about the same size as masonry sand. Wild Bend looked at a really, really high bentonite content for its cement. They put a bag of bentonite with a bag of cement to see if that would reduce the heat of hydration and the cracking. They also went with a 400-pound high solid slurry bentonite, and their dry mix, they went with a 1 part chip, 1 part pea gravel. Once again, trying to match the sizes, and the pea gravel is an inert solids. There's no reactivity to it. It's going to stay at the same condition it was originally created. The 1 part chip we like because it was that dynamic, it would rehydrate. So we're going to see if we can create a high solids dry slurry. Setco went with a real high water content bentonite. They only put a 1-to-1 ratio of sand to bentonite, and they added a lot of polymer, seeing if the polymer would help the bentonite grouts. Then they really cut the water down, and they put in 1 bag of bentonite and 10 gallons of water. Their dry mix, they went by volume. Okay, 5-gallon bucket full of sand, 5-gallon bucket full of bentonite, and it was a 1-to-1 ratio. Baroid is a division of Halliburton. Halliburton's a major cement grouting manufacturer, so they focused on cements, trying to solve our cement issues. And what they did, they really cut down the water content. Bare minimum water, 5.2 gallons for a bag of cement. And then they put in some of their IDP product that would retard shrinkage and reduce cracking. And then they added one that just has a ponzolotic additive, kind of a fly ash component. Their dry mix was a 1-to-1 ratio, only it was by weight. 50 pounds of sand to 50 pounds of granular bentonite. Direct push, folks, they didn't have much choice. They used a 20% bentonite slurry, and they pre-treated their grout with soda ash, and then they left one untreated. And this little tube you see in the picture, that's their grout tube. Now you don't get a lot of solids through a tube like that. It's a pretty small annular space. The ground heat exchanger, we went back to what we did in 1999. You're seeing the picture on the lower right, where we're just free-falling sand through a kind of a bentonite drill fluid. We're trying to recreate a dirty sand, is what we're doing here. And this took a really long time to gravel pack this loop. But it's replicating what the standard was in Nebraska before full-length grout. So here are the results. All right. This looks pretty good. These are 18 recipes. When we dye tested it at Grand Island, we only had 3 of them hit groundwater in an hour. That's pretty good. We had 3 more that are on their way, and by knowing how grout moves, we calculated, we eliminated 6. 6 out of 18 were no longer considered a viable recipe. Well, that's 667. That's pretty good average. And we felt good about that until we went to Pilger. Okay. Now, the northeast site, none of them touched groundwater in an hour. However, we had 7 of them, over 50% of the borehole. We had another 3 or 4 that were over 20% down the borehole. So we've got 10 out of 18 that we've got to eliminate. And that was pretty good. We had late left, and then we went to Trenton. And we had 6 of them hit groundwater in an hour. 3 more, over 70%. But we still had a couple of them that were hanging in there. So we're down to maybe 4 or 5 recipes that we felt really good about in the Vedas zone. Remember the environmental folks? Okay, here they are. Here's their results. Guess which 2 were the 2 they thought would be the answer? That's the bentonite polymers and the bentonite catalysts. And we got 58% and 67% of the grout column compromised in an hour. They were high water content slurries once again. If you look on the left-hand side of the chart, their 9-to-1 sand to bentonite ratio, 24%. And this is an average of all 3 sites. So that's acceptable, but hey, clear over to the left, their dry mix, 3%. They matched a dry borehole with a dry mix, and only 3% of the grout column was compromised. We have found that high solids content in an environmental well, which is mostly all Vedas zone, is the only way to protect that groundwater. A high water slurry is not going to be effective. The direct push, folks, it really didn't matter much. if you treated the bentonite with soda ash or you didn't. That really is just statistically insignificant when you look at over 80% of the grout column compromised in an hour. And the problem with the direct push is they just can't get a big enough angular space to get enough solids in there to protect the borehole. To show you that, this is a video of a monitoring well installed by direct push methods. We're going down a 2-inch monitoring well. You already see the dyes penetrated in front of us. We're coming to static water table. And this is the only time in the study we saw a bentonite crack below static water table. In fact, not only crack below static water table, it allowed dye to penetrate below static water table. Now, to be fair, this is in a kind of a semi-confined aquifer where once you penetrate the production zone, the water table is going to rise up into the clays and the soils. But when we compared this with all the other wells on site that had a large enough angular space, we never saw the cracking and we never saw dye penetration. So the logical conclusion is there's just not enough solids in this borehole in order for this to provide protection. Now, I want to say a word just a minute here about direct push. Direct push is a fantastic technology for what it's designed for. Direct push will come in and give you a biopsy of an aquifer. It'll delineate a plume quickly and cheaply. It's designed for investigations. Okay. Trying to make a permanent situation out of an investigative tool is not going to be effective here in Nebraska. And I'm sure the folks behind this technology are going to adapt. By participating in the study, they found out where they need to get better, and I'm sure they will do that. But for now, direct push is used as a temporary well in Nebraska. Rotary mixes. Okay, this is all the rest of them. This is really interesting. Let's go over here to the chart again. If you stand back and look at the chart, you're going to see dramatic differences right here. Okay? Anything this side of the chart, when you look at it, is a high water content. It's a high water slurry. And look at the results. Over 50% is compromised. And hey, look at here. Drill cuttings. How can that be? This is the same material that came out of the borehole. How come we got 57% compromise off the same material? Well, after looking at this, we came to the conclusion that while it's the same material, we cannot replicate the compaction that this material is placed in. In other words, when you drill it up, you destroy the compaction. When you destroy the compaction, you destroy the sealing capabilities. That's why we don't allow drill cuttings as a grout in the state of Nebraska. But let's go over to this chart. This is how we construct domestic wells in the state of Nebraska. I felt really great about that. Only 10% of that column was compromised. So we know our drinking water wells were pretty well protected. Here's the cement with a fly ash additive, 9%. These two are almost identical. Here's our gravel, 3 parts gravel with 1 part chip. Here's our sand with bentonite, volume to volume ratio. Here's a sand with a cement bentonite. This is a high solids, 1 part sand to chip. Here's the IDP with cement. So high solids contents, we got less than 30% penetration of the Vedas zone. That was a lot of fun. So this is the best video of the whole bunch. This is a nice, tight, neat cement. Look at that. It's got a little horizontal crack. Not bad though. There's not a wrinkle. There's not a crease. There's not a flaw in this thing, man, and water's passing it between it and the casing. Look at that. You bond log this thing. You use the old technology and bond log this. They would tell you that's perfect grout. If you didn't have a visual component, you wouldn't know about a microannulus, and this is where we learned where cements don't bond to PVC. During the heat of hydration, the cement gets hot and it softens the plastic. Okay? When the cement cures and dries, it recedes and draws back, and the plastic goes back to its nominal size. And it creates a microannulus not much thicker than a sheet of paper. But without that bonding, we don't have a seal between our grout and our casing. But we've got great structural stability. So, cement really does not bond all materials like we were told. It really is not the universal grout material like we thought it was. It has some fantastic universal properties. But now we know that there's truths and there's myths about both cements and bentonites. But I want to give you some really, really exciting good news, okay? For our geosystems, our geoloops, the dirty sand experiment worked really, really well. The dye test showed that we only had dye movement of about 5 feet in an hour and no change in 24 hours in that dirty sand. When we went back 30 days later, we didn't see any change. We went back 90 days later, no change. And it provides superior thermal transfer because we have full contact with the loops. We have now solved a problem for our environmental folks, and we have now solved a problem for our geothermal folks. The only thing left to decide here is how to come up with an effective way to place this sand so it's easily placed, so it meets our fourth parameter. And I think we've done that. So this gets us into the unconventional thinking new results portion of the program. Dave Hansen is a past McEllhiney lecturer. He's the owner of Design Water Technologies. And he told me as part of our task force when we first started this, Tom, I don't think you can seal the borehole in Nebraska. I said, Dave, you're crazy. Of course we can seal the borehole in Nebraska. Do it all the time. Man, we would be in big trouble if we couldn't seal the borehole in Nebraska. Well, I studied all the videos. I looked at every one of them. Over 9 years, 128 wells, foot by foot, and it really pained me to say this for the first time because he was sitting in the audience, but he's right. We cannot seal the borehole in Nebraska. You know why we can't seal it? Because the ground we're drilling in isn't sealable. If it was, we wouldn't have groundwater. Okay? If we could seal it, we wouldn't be a groundwater generator. Our state was designed to collect and store groundwater. That's what it does. That's what the unsaturated zone does. And if you put a high water slurry in that filtration system, it's going to take the water out of it and store it. That's what the design is. So rather than fighting against Mother Nature, insisting that Mother Nature do something she's not wanting to do, if we want to protect groundwater in Nebraska, the best thing we can do is protect the filtration system. And when we drill a borehole through it, we can't allow grouts that crack and channel and bypass the filtration. We have to have grouts that divert everything back to that filtration system and let the world do what the world was designed to do. Okay? Reconstructed conditions in the borehole that mirror the surrounding soils in the unsaturated zone, then we can provide groundwater protection. So what's needed? Well, I'm going to tell you a little story again. Told you I was a contractor for 20 years, right? Well, as a contractor, I didn't much care what was between the production zone and the surface, because I got paid when I got to the production zone. That's where the water was at, that's where the money was at. So my well logs didn't pay much detail to the surface geology. That's exactly the wrong thing to do after looking at the results of this study. We have to pay more attention to that geology and the unsaturated zone. We have to write down everything on the well log where it occurs. We have to have the accurate descriptive language telling engineers and designers of wells what we've penetrated, and we've really got to be more meticulous every time the bit starts in the ground. What's the best method for grouting? What's the best material? There really, folks, there's no magic bullet. There's no cookie cutter. There's no material you can say, use this every time, you'll have universal protection. There isn't such a thing. You have to match the grout composition to the on-site conditions, much like we discovered when we put a sand cement in a sand aquifer. Okay? And this will work either if you're in consolidated soils or unconsolidated soils. All right? And there are no shortcuts. If there's any folks out there watching that drill test holes for a living, let me tell you this. You should be the highest paid person in your company. Because if you're a test hole driller and you do the test hole like it should be done and you get the right information and you get it right, everything else is easy. Really is. If you don't get it right, no amount of talent, no amount of engineering, no amount of makeup is going to make up for that lack of information. And in the end, the best application may be a composite. You may have a bentonite, you may have a dirty sand, you may have a cement all together in the borehole. So, in summary, the new truths, and remember this, please remember this. All grout materials are going to perform within their given properties, and they do not change. We tried for 8 years to make a high water slurry work in situations it cannot work. We tried for 8 years to make cement not crack. Okay, I've learned there's two types of cement in this world. There's cement that's cracked, and there's cement that's going to crack. So remember, bentonite slurries, if they can stay wet, if they retain their water, they're going to perform. Inert solids like sands and gravels will improve that performance, but folks, if they crack, they will not rehydrate once they're damaged. Bentonite chips will rehydrate, but they can really be tough to place in the borehole, and it could be a long time to make sure they get down to the place where they got to be. But if you get them placed, they will give you the most dynamic performance of any reactive solids we found. And cements will crack, but cements will give you great structural stability. They will ensure the top integrity of your well, and they have a place in the grout column. But just remember, cements will not bond to PVC, so you're going to have some sort of a bentonite or some sort of other dynamic seal below that. And neat cement has the properties to intrude through chips. So lower the water content the lowest you can. A sand blotter is needed when used with chips. So where does Nebraska go from here other than the Big Ten? They got a lot of laughs in Big 12 country, let me tell you. Our PWS people, based on the findings of this study, now require bentonite chips from just above the screen openings throughout the whole borehole, and the wells must have a surface protection of cement or, if applicable, chips, depending on the conditions. All right? Full-length protection of a dynamic seal we feel is going to protect our towns, our cities, and our communities, giving the best possible protection. For our private systems, we are in revisions of our well standards, and we're going now with some different ideas. We're all focusing on water quality instead of water quantity. We always have had a surface seal, but now we have an aquifer seal. We're going to put a seal down on top of the aquifer as a primary seal. The surface seal is going to be a secondary seal, and we're going to have high solids fill material in between. We're not going to allow anything for closed loop or geo systems that don't have a high solid sand content in them. No longer just a bentonite slurry, because we know they don't work. We're going to look at minimal screening and full-length grouting in areas of high water quality concerns. And there's one more neat little story I want to tell you about Clarks, Nebraska, that we learned. Clarks is a town in central Nebraska, gets its water out of a homogeneous aquifer. It's all sands and gravels, maximum 114 feet deep. Clarks struggled with uranium in their water. So in order to address that, Clarks went outside of town, found a site that had 0 uranium, drilled a test well, and developed it, and wow, let's do this. when they put out their production lines and developed the wells and put in the new city wells. First month they had pretty good results, but slowly but surely their well started climbing up into that 120 picocuries per liter for uranium. Well, how does this happen? How does an aquifer go from 0 uranium to 124? Well, we called back the folks from Direct Push, Geoprobe, and they have a neat little tool that inserts water through the point as they're mapping the aquifer. And they were able to delineate 3 to 4 aquatards within that aquifer that were no thicker than that cell phone. Okay? I told you I was a water well driller, and I was a pretty good driller when it come to production zone, but there's no way I would have found an aquatard this thick. So when they found those aquatards, they constructed integrated wells in a step pattern so they could measure the uranium content. And what they found at the bottom? 0 uranium. The next level up was about 30 picocuries per liter. The next level up was about 60. The top level was 120. Then we got to looking at the construction of the town well. The town well had 80 feet of screen in it, big borehole, and gravel packed the whole annulus. And what we did, we commingled the waters. All right? That was another lesson learned. Homogeneous aquifers don't have the same water quality throughout. We know there's different water qualities in a sand, gravel, bed aquifer. So our standards are looking now at addressing that concern. If we know there's a contaminant, we're recommending minimal screening and full grouting in those areas. We're going to have a steel segment through the frost zone with a cement seal because we're confident the cement will bond to steel. We're no longer allowing any grout slurries without high solids for any reason above the unsaturated zone. And for the first time, we're going to have a uniform grout standard, whether it's for potable wells, whether it's for livestock wells, or whether it's for irrigation wells. We're all drinking out of the same pitcher of our wonderful aquifer, so we're going to protect it in a uniform standard. There are future studies that are coming on the horizon. Now, Nebraska knows what Nebraska needs to do to protect our groundwater. We moved ahead with those standards, and we feel real comfortable about that. But because we have the study laboratory for the nation, our bentonite folks have asked us to consider studying calcium bentonites, pelletized bentonites, cement and steel pipe, and then we're going to look at a process called microcells that I learned about in Australia that they use for their cement solids. And what microcells do is they lighten the weight of the column and they maintain the high solids content. So there are more studies coming. The grout study is published. The University of Nebraska has that for sale at their MAPS room. It's about a $30 charge. The Vedas zone study is not published yet. It will be here in the future. And any other future studies will also be published through the university. Now, I want to tell you something personally. This has been a wonderful, wonderful year for me. It's gone by really quick. And I've gotten so much out of this opportunity to be a McEllhiney lecturer. And I learned early, if you want to make a difference, you get involved. Okay? I'm the type of person that if I go to a meeting when I was a contractor and I didn't like what was being said, I had the right to remain silent. I just didn't have the ability to do it. So I raised my hand. And that got me on a committee. And that committee got me involved with my local health department. That local health department led to being involvement with the state. And the state led me to be involved with the national. And this is how a well driller from eastern Nebraska goes from drilling private wells to talking all around the world about dirt, rocks, and water. You get involved. Because decisions are made by those who show up. That happens every time. If the people that have the experience, the boots on the ground experience, don't show up to these meetings, the planners don't have the benefit of your knowledge. And if we're going to have a new focus on water quality, we've got to start with a good design, focused on that. And we've got to couple that with good construction and a commitment from our industry, commitment to excellence. And if we can do that, we're all going to have a brighter future for the groundwater industry in Nebraska and hopefully other states and the countries around the world that have talked. But it all starts with you getting involved and becoming interested in how you can improve the process. Now, there's a lot of credit that goes on with this. And I want to thank personally our partners of Baroid, Wildben, and Setco for providing the expertise and the products to make this study happen. Without their cooperation, there's no way we can pull this off with all the different dynamics we come up with. I want to thank my state I'm very proud of. When we discovered that bentonites didn't do what we thought they did, my state had the courage to stand up, fund it, back it. Our administration fully went behind it, and I'm very proud of that. And because of that, we came up with new solutions that hopefully help not just Nebraskans, but everyone else that is interested in protecting groundwater. I want to thank the university, the departments of DEQ and HHS for combining the task force and the manpower and dedicating the resources to this. This is a major, major drain on resources, but it has a major, major impact. And I want to thank the NGWA for giving me the opportunity to share this with you out there and folks around the world. And finally, if you don't remember anything else about this lecture, remember this slide. Because this is why we do what we do. This is why I do what I do. And if you can't read the quote, that's from Wally Schirra, a NASA astronaut, that says, 3 times I left the planet and found nowhere else to go. So please take care of the spaceship we call planet Earth. And that sums it up about as good as I can. So with that, ladies and gentlemen, that's the conclusion of the 2011 McEllhiney lecture. And we have people standing by if you want to phone in some questions. We'd be more than happy to answer them. Well, I guess we have no questions, so thank you for attending, and I hope you enjoyed the presentation.